Very good morning, my dear student friends. We will continue with the same problem, whatever I had dictated yesterday, and we have solved all the three parts of that particular problem, and then we were discussing about the process capability and other things. If I recapitulate the things, we calculated or we know what is meant by trial control limits, and then we found out the revised control limits. I think where I stopped at that particular point of time. And two things we could observe there, because naturally there are two things which can be observed if it goes out of control or when we are trying to find out the revised control limits. What is going to happen is either those points which have fallen outside the control limits of R chart only, or some points will fall outside the control limits of X bar chart but not on the R chart, and in some cases, on both the charts, it will fall outside the control limits. In that case, we need to find out the revised value of X double bar as well as R bar. But in our present case, what has happened? The trial control limits on X bar chart were within those control limits. Hence, we never touched about those things. Whereas on R chart, the 2 points, especially the sample number 1 and sample number 3, they had fallen outside the control limit of R chart. That is why we found out the revised control limits for R chart and kept the control limits on X bar chart the same. Otherwise also we could have found out the revised X double bar, which will not vary much. We found out the revised R bar after eliminating these 2 points as R bar is equal to 8.388. Okay. Before this one, it was 9.8. Now, after eliminating those 2 points, the revised R bar value has been 8.388. And even if we had eliminated those 2 points from the X bar chart, then the new X double bar value would have been, that means after eliminating these 2 points on the X bar chart, the new X double bar value would have been 178.511, and earlier it was 178.46. You can see that there is not much difference between these two. Whereas in case of R chart, earlier the value of R bar was 9.8, and after revision it has become 8.388. Here also, after revision it has become 178.511 instead of 178.46. Why? That means there is not significant difference over here. So that is why we can keep 178.46 as it is, or we can use this revised value of X bar chart. Both the things are allowed. That is what I was mentioning in the previous class. There are two schools of thoughts. If any point falls outside the control limit, either on X bar chart or the R chart, those points need to be eliminated in order to find out the revised control limits. Those points will be eliminated on both X bar chart as well as R chart, or whichever falls outside the control limit on one chart, only that can be those points can be eliminated. In these cases, that is what I have shown. So for our purpose, revised control limits, X double value either I can consider earlier only, that is 178.46, or the revised 178.511. Okay, that means even if it is approximated, it also works out to be 178.5, and after approximation, this one will also work out to be 178.511 or 5.5 ohm. It doesn't make much difference if it is going to be one single digit accuracy. If we go, it doesn't make much difference at all. Okay. Having done that one, now the revised control limits are going to be for X double bar or X bar chart. It remains same because I am going to use this one central line 178 point. If you want, okay, we can change this one to 0.511 central line of X bar chart, and upper control limit of X bar chart, it is going to be how much? 178.511 plus A2 R bar. A2 R bar, we have found out the value of A2 because I will write here for n is equal to, for your convenience, whatever, because yesterday this thing only I am carrying forward. For n is equal to 5, A2 is equal to 0.58. D4 is equal to 2.11. D3 is 0. And D2 is going to be 2.326 because the sample size was 5. So A2 value is 0.58. So upper control limit, this is 0.58 multiplied by 8.388. And lower control limit of X bar chart is equal to 178.511 minus 0.58 into 8.388. So this total value, it works out to be 178.511 minus 4.8650. Okay. And this one 178.511 minus 4.86504. This is plus this one, this is minus this one. This will remain as it is. And for R chart, central line 8.388, upper control limit D4 R bar, that is 2.11 into 8.388, and lower control limit, it is 0 into 8.388. So this works out to be D4, we can find out 17.698, this is 8.388, this is 0. Okay, if we calculate the values of these things, that is 17.8, 178.511 plus 4.86504 183.3760, and this one is going to be 178.511 minus 4.8650. Oh, this one works out to be 173 0.6459, and the central line is so much. So we have found out all these things. Now what we have found out? Upper control limit for X bar chart, lower control limit for X bar chart and its central line. Similarly for the R chart. Now if we compare them and if we plot them, that is what I have shown in the previous this one. That means if it is to be plotted, now you can plot it like this. This is the central line. This is the lower control limit. This is the upper control limit for X bar chart. These are the samples. 1, 2, like that. I can take 20 samples I have taken. These are the values I can put here. 183.37. This one is 178.511. And the lower control limit is 173.6459. Similarly for R chart, it has to be drawn just below the X bar chart. Here the lower control limit is 0 of R chart, and the upper control limit to some scale it is going to be 17.698. That will be drawn with the dotted line. This is the upper control limit, and the central line it will be somewhere here. This is 8.388. This is R bar value. This is upper control limit, this is lower control limit, and again the samples are 1, 2, like that. Now if these things are plotted, we'll see that all the values on both X bar as well as R chart, they will be falling within the control limits. Hence, these are to be used. Now instead of 20 values, sorry, it is not 20, now it is 18 values only, okay, because 2 have been eliminated. So these will be falling within the control limits. Hence, these revised control limits itself, they will become the standard control limits for the future production. That means what? You take again the sample of 5, find out its mean, that X bar value, and then try to put it on this graph, these controls, whether it falls within the control limits or not, you can see. If it falls outside the control limit, say not because of not meeting the upper control limit value outside, that means there is a change. That means up till now it was following, but now it has fallen outside, means what? There is a change in process. That is what it signifies. Then that is the time to stop manufacturing and start investigating why this point has fallen outside the control limit. What could be the reason? That is how it goes on. Okay? Now, if we observe these things carefully, certain points can be drawn. Now, because another thing what he has asked is, you have to find out what is the okay, this is okay, he has not asked for sigma prime, but I want to bring in, because here in the third part he has asked, the specified requirements for the quality characteristics are given as 171 plus or minus 11. If a product falls below lower specification limit of 160, it must be scrapped. Whereas if it falls above the upper specification limit of 182, it may be reworked, because scrapping an article is much more costly than the rework. It is desired to hold a scrap to a low figure without causing excessive rework. The process averages can be shifted by a relatively simple machine adjustment. What would you suggest as the aimed at value for process centering in the immediate future, and why? Before that one, whether the process is capable of meeting the requirement or not, it can be found out, which we call it as the process capability I had explained in the previous class. That process capability is equal to six sigma prime. Now, when the process is under control, then only we can find out the sigma prime. So, sigma prime I can find out from this one here, because we know the relationship sigma prime is equal to R bar by D2. Now, the process is under control and R bar we have calculated it to be 8.388. 8.388 divided by D2. D2 is the value from it is a tabulated value, it is 2.326, which will depend only on the sample size. So, the sigma prime can be calculated as like this. So, sigma prime works out to be 3.606. What this one? Why we should find out this sigma prime? Because here in this class, I want to discuss something about the process capability and its analysis, which is going to form a part of the syllabus of this particular unit, process capability analysis. So, I am taking this example itself to teach you about that process capability. So, now we have found out the process capability as, now sigma prime as 3.606. Hence, the process capability for this particular process, it is 6 times this particular value. 6 times this particular value, it works out to be 21.636. 21.636. That already I told you that these are the width of the process limits. So, if you observe this particular problem clearly, we have got 3 limits. Let me take up for X bar chart. We have got 3 limits. What are those limits? One is the specification limit, which is specified by the designer, and it is given in this problem as 171 plus or minus 11. So, the specification limit, it has been specified. It has been specified as, I will just wipe it out. The specification limits we have found, it has been given, that is 171 specification limits, 171 plus or minus 11. That means upper specification limit, upper specification limit, USPL, that is what I will denote it. So, 171 plus 11, that is 182, and its central line is going to be 171, and the lower specification limit. (171 minus 11), that is 160. Okay, this is designer who has specified it. As long as the part has got the dimensions within this range, it will be accepted. The moment it is less than this or greater than this, it is no longer, it is acceptable. And if we look at the control limits we have found out to be upper control limit, central line, lower control limit, upper control limit, it is 183. 376. Center line 178.51. This one is 173.64. These are the control limits we have put. Okay, try to understand. These are the control limits we have put. These are the specification limits. And the process limit, that is what? Natural process limit. These are for controlling purpose, I have put like this. And if I look at the process limits, the process limit is that is upper process limit, central line of the process, and lower process limit. Upper process limit is equal to x bar prime plus 3 sigma prime. This is x bar prime. This is x bar prime minus 3 sigma prime. Try to understand now. These things are to be calculated now. Actual process variation is that this much. Required limits are so much. And I am controlling at this point. If we take up this one, upper process limit, the x bar prime, the best estimator of x bar prime, that is what universal this thing I am using. But best estimator of x bar prime is x double bar. In our case, x double bar is going to be, how much? It is going to be 178.51 plus 3 sigma prime. Sigma prime I have found out to be 3.606. 3.606 multiplied by 3, if I take up 10.818, that is 10.818. So the upper this thing, it is going to become 178.51 plus 10.818. $189.328, and center line is 178.5, and lower specification limit is process limit is 178.51 minus 10.818. So this is going to be 178.51 minus 10.818. This is equal to 167.692. Try to understand. Now what is happening? Right now the natural processes they are varying between 167.692 to 189.328. Required things are 160 to 182. Okay? And control limits are between 173 to 183. You try to observe these things carefully. Okay, that is what is most important. So I will list down here the upper specification USL process limit is equal to 189.328, central line of the process This is 178.51 and lower process limit value is 167.692. Because the other things are not required for us, because R bar and other things only they are limited for this, the drawing the chart and other things. Real crux is here. These are the process limits. What is happening now? If you observe, what is happening? Here, some of the parts, they are going to manufacture 189.328. After manufacturing, we can find. It can never be greater than this. But whereas the required thing is 182, that means if I leave it as it is, the parts are being rejected for not meeting the upper specification limit, or more rework has to be done. Do you get this one? Presently, more rework is being done. That is what it means, analysis. Here, lower specification limit is 160. The lowest I am going to get is 167. It will not be lesser than 167. That means 166 and 65, it is not manufacturing. But even though it is allowed up to 160, what does it mean then? What the process is going to do? How it is behaving? That means now they have centered it as 178.51 to avoid the rejection due to scrap. They have seen only that aspect. No scrap is being produced with the existing thing, right? But there are more rework. If you want, we can find out what is the percentage of the rework. That will also I will show you in this example, taking this example itself. Because then only you can comprehend all the things. Instead of taking up some other example and explaining that one, let me take up the same example and explain you all the things. So, if I denote it like this, say for example, what is the process now? The process is following the normal distribution. Okay, like this. Its center is here. What is this value? This value is 178.51. And I have taken the 3 sigma values. 3 sigma values from this one plus 3 sigma prime. Process limit only we need to consider. Because try to understand, when we are considering about the percentage of the items falling or being produced, then I am going to use the natural process limits. These are the natural process limits. And if we talk about the control charts, these are the control limits. The difference, still I have not made it clear to you. I am just trying to tell you this one, and then I will come back to that one short while from now. Okay. Now this is 178.51 and the upper process limit, this is going to be how much? 189.328. Lower process limit, it is 167.692. Is it understood? These are the process limits. Where are the specification limits? Because that is what design, this is what the whatever inspector, whatever is there, he is going to compare with respect to this. So these limits are going to be, one is at 182. The another one is 160. 160. What this one? If it falls beyond this one, because here if you look at it, all the values are between 167.692 to 189.328. No values is lesser than 167.692. That means virtually it is meeting the lower specification limit. That means no scrap is being produced, is meeting that. But if you look at this part, many components have got the dimensions more than 182 units, 182 mm, more than that. What percentage? That we can calculate. That means it can go up to 189.328. It is natural. This is the natural tendency of the process. This is the natural tendency. And if you look at this one, this will become 6 sigma prime, and this 6 sigma prime value works out to be 21.636. Try to understand this difference if you like it. This works out to be 21.636. And if you look from this point of view, the difference between the upper specification limit and the lower specification limit, 182 minus 160, it works out to be 22. And if you look at this one, the difference between this one, 183.376 and 173.64, so approximately it is 10 mm this difference. Here the difference is 21.636. Difference which can be tolerated is 22 mm. That means you can see now it should be what? What is going to happen? If something is which limit has to be more, which limit has to be less or equal to, those things we are going to discuss. Now in the present these things, that is what we have concluded, that no scrap is being produced, but there is excessive rework. How much percentage of rework? We have to find out. How do you find out? Because here we assume that it follows the normal distribution. Then if it follows the normal distribution, then we can make use of the normal table and find out the percentage of the items. So to find out that one, I need to make use of the standard normal table. If I want to make use of the standard normal table, I need to find out the standard normal variate. That means standard normal variate, I need to find out, that is Z value. Z is equal to standard normal variate. Z is given, it can be calculated by X. This is the desired value minus mu divided by sigma prime. I could have used here X double bar or X bar prime. Okay, because X double bar is the best estimator of X bar prime. Okay, here I cannot use sigma X bar. No, it has to be sigma prime. That is what we have found out. This is the desired value. That means this area I want to find out. Presently it is being, this is the rejection, is it not? If it is more than 182, it causes the rejection. That means this value I will put it as 182 minus X bar prime 178.51 divided by sigma prime. The sigma prime value is 3.606. Okay, this is the Z value I have to calculate, and from this thing I need to find out the area. Okay, so now 182 minus 178.51, this is equal to 3.49 divided by 3.606 divided by 3.606. This equals to 0.96, 0.967. Try to understand this Z value can be positive or negative or 0. So you need to be particular about this one. This is positive. If x bar prime were more than this value, then it would have been negative. For that one also area we can find out. So this is the Z value, 0.967. Corresponding to this Z value, what area we are going to get? Let us see from the table. So corresponding to 0.967 plus 0.96 this table, something wrong, he has given 0.96. It should have been mentioned as, it should have started 0.96, okay. 0.823, 0.823, which is the area from, because if we refer this table, it gives, this is the 0 it considers, and this is the desired value I have put it, and up till this one area, that is what it gives. This area included, this from here to here, the area included, from here to here, it is area included is, that is what it is going to calculate. Or this table, if I refer, it has got two ordinates I need to have to find out the area, two ordinates. One ordinate is, it starts from minus infinity. So from minus infinity to this area I can find out. That area I have found out it to be equal to 0.82 and plus 96, 8238, 0.8238. That means from minus infinity to this one is 0.8238. But I want beyond this. That means total area I know it is as 1. 1 minus 0.238. That means approximately 1 minus 0.8238, approximately 18% the defective items are being produced now. Defective in the sense 18%, I can say that 18% of the items are being reworked. There is no scrap, but 18% of the items are being reworked. That also he says, the reworking also it costs something. That is what he says. Lower specification, it may be reworked because much more costlier than rework. It is desired to hold the scrap to a low figure without causing excessive rework. Now there is 18% is excessive rework. So is it possible to reduce? That is the question that is being asked. Now what I have found out, I have shown you that presently no scrap is being produced, but 18% of the items are being reworked. Can you reduce that? And he has given the clue for that one in that question itself. He says, the process average can be shifted by relatively simple machine adjustment. That means if you look here, now the process is centered at 178.51. And I told you, because this dispersion, I cannot do anything about it. The dispersion is going to be, that is 6 sigma prime, that is going to be 21.636. Whether I shift, centering is now like this. If I shift it, now the centering will become like this. It will become like this because it will be shifted. This value is being shifted to this value. That means you want it, the average to be more towards this one or towards the lower specification limit. No, always, because now this is the thing, it is to be towards the lower specification limit. How much I can reduce it? I will make this what upper process limit, it should coincide with the upper specification limit. I will adjust in such a way that upper specification limit and the upper process limits are going to be same. In that case, what I can observe is only 0.0135% of the rework can be done. Not more than that. Try to understand. From 18%, we can reduce it to, okay? We can reduce it to 1% hardly. That is what you can think. Okay? So much colossal, the waste has been reduced and it can be got. This is the crux. So, how do I say this one? Because then we need to observe why did I find out 6 sigma prime. 6 sigma prime is to be compared with difference between the upper specification limit and the lower specification limit. Or you can say that these are the maximum values and the minimum values of any product. Minimum should be 160 and maximum should be 182. So that difference we can get it as 22. And process limits, if I look at this one, this is 21.636. So 21.636, it is what? 6 sigma prime. So I can put in some equation form. Okay? What is the maximum dimension? X max. Minimum dimension? X min. This difference minus. This can be compared with 6 sigma prime. How do I find out X maximum and X minimum? These are nothing but the specified limits. This is X max is upper specification limit and this is lower specification limit. Okay. In this case, it has become 182 minus 160, so it is 22. And here, 6 sigma prime, I have got 21.636. Now try to understand. This one, I have not put any value here in general, because I may have equal to sign, less than, or greater than, which is advisable. That is what we need to think. That means this relationship, it may be in 3 ways. It will be like this. That means this difference, whatever is there, it might be greater than X max minus X min is greater than 6 sigma prime, or X max minus X min is equal to 6 sigma prime, or X max minus X min is less than 6 sigma prime. Which is desirable? What is going to happen? Just try to see here. Okay. Now, this is the maximum variation. This, if it is greater than this variation, what is going to happen? That means naturally it is producing all the good components. Nothing is being produced or nothing is defective. No defective items are being produced. That is what it shows us. Okay. This is what? That means this is more, and compared to this one, this 6 sigma limit is less. So no rejections will take place. All the good items are produced. If it is more than this, okay, then that is the case. Now in this present case, what has happened? It is almost equal to this. See, 22 difference, 21.636. It is almost same. It is equal to. That is stringent. That means if I shift this one over here, yes, it is possible to reduce the rework or the scrap. To what limit I can change it? The best thing would have been, it should tally with this one. What I will make, its upper process limit, it should coincide with this one. Then I can find out the sigma value. I know from there I can find out the x bar prime value. What I will make, the x bar prime plus 3 sigma limit is equal to 182, and then find out the value of x bar prime. Or in case you can say that almost it should be in middle with this. But if it is made as 171, yes, 171, what is going to happen? That also we have to see. Almost in the middle is going to happen. In that case, since it is very close, some scrap will be produced. That is what, in this case, what I will do is, I will make the upper process limit is equal to the upper specification limit, that is 182. Okay? That means mu bar prime plus 3 sigma prime should be equal to 182. And I know what is sigma prime. Hence, the process average value is equal to x double bar or x bar prime is equal to 182 minus 3 sigma prime. That would give me the changed value to what the process value, the process average has to be shifted. Okay? But try to understand, if it is the thing, then close monitoring is required. The process is sufficient to meet, just sufficient to meet the required specification limits. Here in the first case, if it is like this, it is more than adequate process. More than adequate. We need not have to bother much about it. Okay? That means we can be relaxed. Here it is just sufficient, but the close monitoring is required. If x max minus x min is less than 6 sigma prime, then this is the cause for worry. Whatever you do, it is inevitable that the defective items are being produced. We got to live with that. Or if I want to change, then I have to change the process itself. Process itself, that is what I told you. We need to go existing machinery, you change it to the new machinery. Some overhauling is to be done. Or the person is not properly trained. He should be properly trained. That the existing process needs to be changed. That is what. Okay, that is what it gives. So the happy situation will be this. Okay, this is how we can compare the process capability. This is nothing but the analysis of process capability. Through this example, I am trying to tell you about that. Now coming back to this example and answering that question, that is C part, to what the process average can be shifted by relatively simple machine adjustment, what would you suggest as the aimed at value for process centering in the immediate future? Because now 18% defective items are the rework is being carried out. So I will shift the process average from this one to such a level that this level In that case, the upper process limit, whatever is there, it should be made coincidence with the upper specification limit. Upper specification limit is 182. Okay. So this one, what I will do, then hope you have understood about this one. Now I am going to answer this particular part. Now what I will do, I have to change the process average. What I will do, I will make this one the upper specification, the upper process limit is equal to upper specification limit. And I will not make lower process limit is equal to lower specification limit. Okay, in that case, I am going to produce some more thing, some more defective parts, rework. No, not rework, it is to be scrapped. It is better to reduce the rework. Excessive rework is being done. It is better to reduce and at the same time take care that no scrap is being produced. Okay. So here what I will do in that case, new process average, how do I find out? I said upper process limit make upper process limit is equal to upper specification limit. What is the upper specification limit? Upper specification limit is 182. Okay. So now what is the upper process limit? Upper process limit is x bar prime or x double bar plus 3 sigma prime. And this sigma prime, it cannot be changed. That sigma prime is going to be 3.606. That means x double bar plus 3 into 3.606 is equal to 182. Or x double bar is equal to 182 minus this much, 3.362. That is going to that is going to be it works out to be 3 into 3.606. This is equal to 10.818. X double bar is equal to 182 minus 10.818. That is 182 minus 10.818. So it can be set to 171.182. Try to understand. If you set it to 171, some scrap will be produced. That is because it is very close. The limit, the difference between upper specification and lower specification, and the difference of the upper process limit and lower specification are very close. Okay. That's why this is most important. That is why we can set it to 171.182. In that case, the no scrap is produced and the rework produced will be very less. Okay. I think if you have understood whole crux of this one, I'll take up one more example in the next session, and that will complete the portion of control charts for variables. So tomorrow class will be the concluding class for control charts for variables. Okay. Good. Thank you.